Hello, this is Joel. This type of biasing is called phase bias or class A amplifier. As you can see, only two resistors are being used. This resistor here is called RC, the collector resistor, and here is called the base resistor, RB. And since this type of design, the voltage supply, whatever we supply, is also our output, that is VC. VC is from the collector pin of the transistor and the positive supply rail of the battery or whatever. Then the base voltage also is the base pin, and the voltage supply will give us the VB, base voltage, or the voltage across this resistor will give us the value also. So since this is directly connected to the ground or the negative supply, it has 0 on it, 0 volt. So let's say we want our load or RC to drain or draw about 40 milliamp of current. So since we know our VC is also equals to VS, our VS is 10 voltage supply. So since we know our voltage supply is equal to the voltage output, so which give us this, and since this emitter pin is directly connected to the ground, it has 0 volt, which is VE equals 0. Now let's now calculate. Since we know that the voltage supply equals to voltage out, 10 volt voltage supply is equals to voltage out. Now we want to calculate the value of resistor for the RC. Since voltage supply is equals to collector volt, collector pin, and the positive supply, so 10 divided by the current we want to flow across this resistor, 40 milliamp, divided by 40 milliamp will give us 250 ohms of resistor to be placed in here. The standard value of resistor we can get is 220, but since we are going to use simulation to confirm, 250 ohms. And VB, the base voltage across this resistor, is known as VB. That means the base pin and the positive supply. VB is equals to VC. Since VC is equals to VS, VB equals VS or VC minus the voltage drop. For silicon type, it is 0.6 minus 0.6. That means 10 volts. That means our supply minus 0.6 will give us VB, which is 9.4 volts. And to calculate for the current and the resistance, we make use of this. Let's say we want the magnification of our IB current to be 100 times IC. So we make use of this. IB is equals to collector current over frequency current gain. Our IC is 40 milliamp. 40 divided by 100 current gain will give us about 0.4 milliamp of current flowing through this resistor. And now to know the value of resistor, we just need to divide the voltage using Ohm's law. 9.4 volts divided by 0.4 milliamp of current from here, IC over current gain 0.4 milliamp will give us about 500 ohms. That is about 24 kilo ohms resistor should be placed in there. Now let's simulate. That is all for it. For this type of biasing, now since we now know all of this, Now we can now calculate for the current flowing across the emitter pin. So since this is I E is equals to IC plus IB, the current flowing across the IC, the collector current and the base current will give us the emitter current. So 40 plus 0.4 milliamp will give us about 40.0 milliamp will flow through our IE emitter. So let's simulate. Now here I'm making use of circuit wizard. Hello. Now this is it. With circuit wizard I have designed it. What we did here in our calculation. So yeah, let me change the background. Here we can see it is 23.5 kilo ohms, and here it is 250 ohms, and we are using a BC547 and the voltage supply which is 10. Yeah, for the RB you can see, and the RC 250 ohms, and the VE emitter, a current meter to check. Now let me start the simulation. Now we can see from the VC 250 ohms, 9.89 volts, which is equal to the voltage supply, and the current 39.56 milliamp, approximately 40 milliamp from our calculation, 40 milliamp, and the VB is 9.23. That means this voltage drop in this simulator is about, let's say, 0.7 or 0.8 if we have 9.23 volts here, and the current which is approximately equal to it also, and our IE, the emitter current, is 39.96 milliamp. So we see it's about it. Thank you. My name is Joel. That is it. Hello. Here is another type. Another type of amplifier. Now, as we can see, this type of amplifier makes use of RE instead of connecting it directly to the ground. So it makes use of RE. This type of amplifier or this type of design is called fixed bias with emitter resistor. So, and now this is the type of design where you can select half the voltage supply or more than half or up to the voltage supply. Also we can let the output, we can choose the output from any of these, either from RC or from RE, but I like taking my output from here. But though for NPN transistor, IE is always greater than IC and IB is lower than IC. So as we see now, to bias this is almost similar to that but different. Now as we see, now the next thing we need to do is everything here are unknown. So let's say this is where we can now select the half the voltage supply. Now as you can see it is 20. Let's say we want it to be half, so the half is equals to 10 volts. Vc. So our Vc is 10 volts, half the voltage supply to swing to RC. And note that anything you do to RC will also affect or will also show in RE. And this is where you need to use this Vc, that means the collector pin and the voltage supply. Now my emitter now VE is from the emitter pin of the transistor and the ground will give you your VE, the base pin of the transistor and the voltage supply positive rail will give you your VB, positive rail and the collector pin VC. My VCE is from the collector pin and the emitter pin. Sorry, this is an NPN type of transistor, NPN, and the emitter pin is my VCE, and my VCG is the collector pin and the ground pin. That's why I name it or call it VCG, VCE, and VB. So, or VBE, VB, and C pin. That's how it is done in mine. So VC equals voltage supply. Sorry. VC is equals to base volt. The base volt you can see is different from the first type of design. Now, VC is equals to VB plus V drop. That means 0.6 for silicon type of transistor. The base and the emitter voltage drop is about 0.6. I like using V drop instead of VBE, V drop. And now my VB base voltage equals VC plus V drop. Sorry, I was called by my mother. Now I like using V drop for base and emitter. The constant for silicon type is 0.6. So, and this is where I'm checking it. I formulated everything. So in my earlier video you will see it also. So, and now VE is equals to voltage supply minus VC. That's why I said anything you do to VC you also get in VE from this emitter volt. Remember I told you emitter pin and the ground is my VE, my VCE is collector pin and the emitter pin of the transistor, my VCG is the collector pin and the ground pin is my VCG. Now using this we can now calculate for almost everything, and still our still remains the same, IC plus IB. Using this we can get almost everything. Or let me bring my whole book. Now sorry, BB is not that so now let's continue. Now as we said, our VC to be half the voltage supply, which is 10 volts. Now we need to put in 10 volts to know our VB. Let's calculate for VB first. Since we don't know VB, so we cannot use this first one. Since we know VC and V drop, that is silicon type voltage drop is 0.6. So we can now calculate VB is equal to our VC, we said is half the voltage supply, 10 volts minus 0.6 V will give us VB is about 9.4 volts. 9.4 volts. Now we now know the volt, not the current. We cannot check for this. There's no need to check for this because this VC is equal to VE also. So from this equation, it is also equal to it. So we also have our VE equals 10 volts. 10 volt the voltage supply. Half the voltage. So if we now know each of the voltage, so let's write it out. VE is equals to 10 volt. VC equals 10 volt and VB equals 9.4 volt. And I know the voltage, and let's just say we want about 30 milliamp of let's just choose 30 milliamp of current to flow across the RC, RE and IB are still unknown, but this is the load. So you can use this whereby our IB equals IC over HFE, current gain. To swing, we supply little current, and what we notice, a magnification just occur between the two pin and then supply it out to the collector pin. So IC over current gain, and I said let our IC equals, let me write it down, IC equals 30 milliamp. Now 30, let's still choose 100, the current gain, milliamp over 100. Current gain has no value, so it is 0.3 milliamp of current that need to flow through IB to give us 30 milliamp. Yeah, very low current. You see, 100 IB times 100 will give us our IC. Now, as you can see, the current is being magnified at the collector pin. Now, the next we need to know, since we know the voltage and the current of VB, we can still leave that aside. Okay, let me calculate for the resistance. And 9.4 volts from the voltage drop, 9.4 divided by the current 0.3 milliamp will give us R, and our R is equal to 3133.30. Okay, let's forget the point, let's forget the decimal. 33 ohms, forget the decimal, that is about 31 kilo ohms equals 31.3 kilo ohms approximately. So 2 in one decimal place, so it is 31.3 kilo ohms. Now we can now calculate for RC also, because we now know VC and IC is 30. So RC equals VC over IC. So 10 volts, remember we make it half the voltage supply, and the voltage supply is 20 volts. So 10 volts divided by our IC current 30 milliamp. So our resistor is, let me calculate, equals 333.3 ohms approximately in one decimal place. 333 ohms of RC, and you see 31 kilo ohms will be placing here. Now to know our IE, so we can calculate for the RE. So we use this IE is equal IC plus IB, and our IC equals 30 milliamp plus IB is 0.3 milliamp plus 0.3 milli. So our IE is 30.3 milliamp is our IE. Now we can now calculate for the value of resistor or the value of resistance. Now, using Ohm's law also, VE over IE is equals to RE, and V is 10 volts. Our IE is 30.3 milliamp. So our RE equals, now from the calculator, our RE is 330. Let's forget that. So 330 ohms is our RE. Now we should design this. Now everything is now known. Now for the PT, in my earlier design, checking about, if you guys remember, I told you I want to know the power in a transistor. So in my earlier design, I have gotten the power in a transistor, the formula for it. So I still remember, got it recently. So PT, transistor power, is equal to PBC plus PBE. It gives us the transistor power, and it gives us the transistor power. Now to get PBC and PBE, you see, have to use this. Now to know our VCE, that means the collector pin and the emitter pin, we make use of this from my formulated equation. Shit, I'll pick it. VCE equals VCG minus VC minus the voltage supply, that's 20, will give us our VCG, collector and emitter volt. Now to know the VCG, and so let's continue. To know VCG, VBG first equals VS, voltage supply, minus VB equals VBG, and VS minus VC equals VCG. So we now know VCG, and we know this, and the voltage supply, so we cannot get VCE. VCE, remember, it's the collector pin and the emitter pin. So VCG and VCG also equal the VB minus VC equals VCG also. So, or we can still use this, VCE equals IC, open bracket, RC plus RE, emitter. VCE is equal to IC open bracket, RC plus RE will give us the emitter. So that is it. Now let's simulate and see. Using all of this, we cannot get everything. Now I have finished designing it in the simulator, electronics workbench, and circuit wizard. This is the 20-volt supply, and our value of RB is 31.3. In my calculation, it is 31.3. Battery empty, 31.3 kilo ohms, and our RC is 333 ohms. Our R is 330 ohms. Let me show you the RE first. 330 ohms. 330 ohms. And VCE and VBE also are taken. So this is VC, 333 ohms. Now let's start simulation. Now we can see our VB is still 9.29 volts. Remember, our VC is still VS is still the same. The current, the voltage is 9.23. VE is also equal, as you can see, 9.95 VE, and our VC also is 9.95. So we see it is the same thing also. It is the same thing also. So we have it here. As you can see, I have the voltage supply. This one is for VCG and a ground. So let's switch it on. You see, it is 10.5. That is approximately half the voltage supply also. And here is emitter and collector pin. So we have 95.17 millivolts flowing across it. So that's it. Thank you. My name is Ray. And now to calculate the power, just do all that is written there. If not complete, I'll later post it. Thank you. And IE 30.16. Our IE is 30.3 milliamp. But let's see. Need to leave it now. So, as it 30.16, switch it off, and thank you. My name is Joel.